Welcome to another video. I got this problem from some Olympiad from, I think the country is Kazakhstan. It is to find all prime pairs P and Q such that P cubed minus Q to the seventh is the difference between P and Q, P minus Q. So, I'm thinking, if you look at this very well, Q must be a small number compared to P, because there is no way you can have this difference balancing out with the difference between a cube and a seventh power. So I'm thinking P must be greater than Q, or the difference has to be at least 2, because that's the minimum gap between two prime numbers, except if we're dealing with 2 and 3. So this question brought a lot of questions, but I was able to answer them. Let's get into the video. So the first thing we're going to look at is, can P and Q be the same number? Can they be equal? Well, it's not possible, because P minus Q will be 0, but this cannot be 0, right? The only way this can be 0 is if P is 1 and Q is 1, or if P is 0 and Q is 0. But whether P is 0 or 1 does not make it a prime number. Remember, there must be prime numbers, so it's not possible. And if there are any number greater than 1, this cannot be 0. Okay, so we know they cannot be 0. I don't want to spend time on that. Now, I also claimed that P must be greater than Q. Is that true? Well, see what I'm going to do. I'm going to say that if I move P here, if I have P cubed minus P, I have to write small letter p, come on, equals Q to the seventh minus Q. But one thing I know is that because P is prime, P is greater than 1. And because P is greater than 1, P cubed minus 1 is greater than P cubed minus P. This makes sense. When you're subtracting less than what you're supposed to subtract, your answer is going to be bigger. So this is bigger than 1. But we said P cubed minus P is equal to this, so that means P cubed minus 1 is greater than this, right? But we know P cubed minus 1 is equal to Q. If we factor this out, we're going to have Q to the sixth minus 1. Okay, I'm just trying to save space here. So P cubed minus 1 is greater than Q times Q to the sixth minus 1. We can easily see that. Okay? In fact, we can claim that P cubed minus 1 is greater than, if we drop this integer, remember this is a prime number, so it's more than 1. If we drop it, we can clearly see that Q to the sixth minus 1 has to be smaller than this. And we know that Q to the sixth minus 1 is even greater than Q cubed minus 1. So P cubed minus 1 is greater than Q cubed minus 1, which implies that P is greater than, look, P cubed is greater than Q cubed, which means that P is greater than Q. So in everything we're going to be discussing, we have to know that P is greater than Q. In fact, because both P and Q are prime numbers, the minimum gap between P and Q has to be 2. Otherwise, we already have one of the answers, because the closest prime numbers are 2 and 3. So we have to claim if P is greater than Q, then Q must be 2 and P must be 3. But we know that cannot happen. Okay? Let's quickly say that. Since 2, 3 is not a solution, then P must be greater than or equal to q plus 2. The gap between p and q must be more than 2. How do we know this is not a solution? Well, we can just test it and plug it in. If I plug in 3 here, if I say 3, p equals 3, this is 27 minus, 2 to the 7th is 128. So 27 minus 128 is negative 100 and something, okay? Negative 101. Well, this is just 3 minus 2. This is positive. So this is negative, this is positive. It does not work. So we know this pair is not a solution. So any other pair we choose will be with a minimum gap between any two prime numbers will be 2. So that's why p is greater than q plus 2. Greater than or equal to. Okay, that's going to come in handy. So let me box all the claims. P is greater than q. P is greater than or equal to p plus q plus 2. Okay, so so what I want to do now is try to manipulate this relationship, or maybe I should start from here. Okay, from here, notice p times p squared minus 1 will be equal to q times q to the 6th minus 1. This is the key to solving this problem, because already we know p is greater than q and p must be at least 2 more than q, okay? Now, because p is, listen, this is an integer, this is an integer, and these two are relatively prime and they're not equal. Well, can they be equal? I already took care of they're not equal, okay? So, because they're not equal, q cannot divide p because p is prime. And p cannot divide q because q is less than p, okay? A number cannot divide a number less than it. So we must say p divides this, q to the 6th minus 1, and q definitely divides p squared minus 1. That, by the nature of the primeness of p and q, these two facts must be true. Now, from Fermat's little theorem, we know that when you write any number like this, this number is always a multiple of 7. Always, because 7 is a prime number, okay? Any number that is relatively prime to 7, unless q is 7, okay? Unless q is 7, this number is divisible by 7. Anything you plug in here for q is divisible by 7 if it is relatively prime to 7. That is, it is not a multiple of 7. Okay, the same thing. If any number is not a multiple of 3, if you plug in for p, the answer you get will always be divisible by 3. Okay, let me show you. I don't want to write it. Okay, by Fermat's, I don't know if it's even relevant, but it's important because it gives us a good starting point to start guessing. By Fermat's little theorem, a to the p minus 1 is congruent to 1 mod p, okay? Where a is not a multiple of p. So here, this implies that a to the p minus 1 is congruent to 0 mod p. So we know the way this is 3 minus 1, because 3 is a prime number. P to the 3 minus 1 is a multiple of 3. If p and 3 are relatively prime, and we can already tell because unless p is 3, okay? Now if p is 3, we're going to have a problem. But let's say q divides this. Q divides a multiple of 3. So this is clearly a multiple of 3. Therefore, q to the 6th minus 1 is 3k, and, sorry, is 7k. That's 7 minus 1. And p 2 minus 1 equals 3m. Okay, where m and k are integers. That's all I wanted to say. Okay, so at this point, I can connect this with this and say that q divides 3m. When a prime number divides a product, the prime number must divide either of the two numbers, especially with this 3. And if a prime number divides another number, which is a prime number, they must be equal. So this means that q must be equal to 3. That's one option. Or q must divide m. So m must be another prime number or a composite number that is built on primes, one of the primes being q. Okay, so this is the possibility. We can have q equals 3 or q divides the other integer, which we don't know. However, I'm going to make a claim that q is actually equal 3. Claim q equals 3 and q is not greater than 3. Okay, how do I write that? Q is not greater than 3. So we've said that q is not equal to 2. And now I'm claiming 2 equals 3, and 2 cannot be another number greater than 3. That means we're done if I can prove this. We just know that q equals 3. Proof. Suppose q is greater than 3, then q is greater than or equal to 5, because that's the next prime number that we need, okay? If q is greater than 3, then it must be greater than or be 5, right? Okay, now we need something. Just hold on to this fact, Observe that we said p divides this. P divides x to the, not x, p, q divides q to the 6th minus 1, right? We might as well factor this out, that p divides, if we factor this out, we're going to end up with, let me do the math work here. We can write this as the difference of two squares, q cubed squared minus 1 cubed squared. So we can have it to be q cubed minus 1 cubed, q cubed plus 1 cubed. And we can treat this as the difference of two cubes and sum of two cubes. This factored out will be q minus 1 times q squared plus q plus 1. That's the factored form. So p must divide q minus 1, q squared plus q plus 1. When we factor this one, we're going to get q plus 1, q squared minus q plus 1. Okay, so it means p must divide one of these four. Okay, we know that p cannot divide a number smaller than itself. P is already greater than q. If you now subtract 1, it's smaller. So this is not an option. This too is not an option because the difference between p and q is more than 1. It's at least 2 from this claim. So we have eliminated these two options to consider. So the third options to consider are this number and this number. Okay? So let's go back to this claim. Okay. Suppose q is greater than or equal to 5, then we're going to have p must divide this guy, 5 squared plus 5 plus 1. That is, p must divide, what's this number? 25, 31. Okay? So P must divide 31. Well, because 31 is prime, we might as well say P is 31. Or P must divide this one, 5 squared minus 5 plus 1. So P must divide, what do you have here? 21. 21 is the product of two primes, so P must be 3 or 7. We already said P is not 3, so P must be 7. Well, 7 is showing up here, remember? So P is either 7 or it is here. The answer is beginning to show up. So the problem with these two statements, that P divides 31 or P divides 21, is that P is much bigger than these two numbers, so it cannot divide it. How do we know it's much bigger? We go here. Remember we said that P minus Q, P is greater than Q, so that means this side is positive, this is positive. So we know that, but let's go this way. P cubed minus Q to the 7th is greater than 0. If this is greater than 0, that implies that P is greater than Q to the 7/3. Okay, if we take the cube root of both sides. So with this fact established, we could say that what do we think P is? Okay, because if we can show that P is greater than either of these two numbers, that means these things cannot happen. Okay, so we come back here. If Q is greater than 5, then Q greater than or equal to 5 implies that P is greater than or equal to 5 to the 7/3. If you plug in 5, well, this answer here will not give you a number less than either of these. How do we know? Well, this would be equal to, if you find this is going to be 5 to the, how many 3s are in 7? We got 2, 1/3, right? That's going to be 2 times 5 to the 1/3. Okay, because when you multiply it to be 2 1/3. Okay, so this is P is greater than or equal to 25 times 1/3 of, this is around 1.7, so we can use a good number, we can say 1.5. Okay, so which is equal to just 37.5, I believe. I don't know if I'm right. Yes. So P is greater than or equal to 37.5. So P cannot divide a number that it is greater than in either case. So I just showed you that it's impossible for P to divide this or to divide this if Q is greater than or equal to 5. But if it is not greater than or equal to 5, then it will divide one of these numbers. Therefore, Q equals 3. That is it. It cannot be 2, it cannot be 5, or any number greater than 5. So let's just plug it in. Therefore, P divides 3 minus 1. What's the next number? 3 squared plus 3 plus 1, 3 plus 1, 3 squared minus 3 plus 1. Okay, so P must divide one of these numbers. Let's get all the numbers out. This is going to be 2 times, this is 9 plus 3 plus 1, that's going to be 13. This is going to be 4, and this is going to be 7. 9 minus 2, 7. Okay, so P divides all of these. By the way, P has got to be a prime number greater than 2, okay, greater than 3. We already said that. So it's either 7 or 13. 7 was already clear right from here, that 7 is part of the possible solutions. The other one is 13. So let's just try it. Check. P equals, let's do 13 first. Well, P equals 13 is the answer, okay? Check it yourself. P equals 7 doesn't work Because just mentally looking, p equals 7 tells you that this is 7 cubed. 7 cubed is 7 times 7 times 7, that's 343. This is going to be 2 to the 7th, 128. 343 minus 128 is more than 100. And here, this is just 7 minus 3. 7 minus 3 is 4. So this is 100, this is 3. That's not an equation. So 7 is not valid. But for 13, when we cube 13, let me do my manipulation. P comma Q equals 13 comma 3. That's the only solution because there are no other options for Q, and because it's an equation, there are no other options for P. Never stop learning. Those who stop learning, stop living. Bye-bye.